Welcome back to mass transfer operations 2. We were discussing on adsorption and ion exchange. In the last class, we have discussed on the fluidized bed and teeter bed and steady state moving bed adsorbers. And now we will be discussing on the unsteady state fixed bed adsorber followed by this ion exchange, that is the last topic of this chapter. Okay. So, in unsteady state fixed bed adsorbers, as increasing amount of fluid are passed through a stationary bed of adsorbent, solid adsorbs increasing amount of solute, hence the unsteady state prevails. Or in realistic approach, we can say, if a fixed bed adsorber is there and adsorber is packed with the adsorbents and the say adsorbent is passed through this bed, then the layer by layer the adsorbents will adsorb the adsorbate, and then we can say at any time t the solute concentration or target component concentration throughout the bed will remain ununiform, or we can say it will decrease from the entry point to the exit point of the fixed bed adsorber. So, there are so many applications in the industrial level, like say we can say recovery of valuable solvent vapors from the gases, then dehydration of the gases and liquids, then decolorization of the mineral and vegetable oils, and concentration of the valuable solutes from the liquid solutions, and there are so many more applications of the unsteady state fixed bed adsorber. Okay. So, this we know this one, that this adsorption process actually and adsorption isotherm indicates the capacity of uptake of the solute by adsorbent and at equilibrium under a given set of physical conditions like temperature, pressure and concentration. But isotherm does not speak about the rate or we can say kinetics of the adsorption. Only it can say that say in the equilibrium condition, how much amount of the solute can be trapped by the adsorbent. Okay. So, the rate of this adsorption in a this fixed bed depends on firstly the resistance to transport of the solute from bulk to the adsorbent surface through the stagnant film of the gas, and then resistance due to the diffusion of the solutes through the pores, that pores may be macro porous, may be mesoporous or microporous of an adsorbent like this. So, these two we can say this one factors we can say controls the adsorption rate in the say fixed bed, or we can say this one in the stacked bed. Okay. Now, we can describe the physical description of the adsorption process by mass transfer zone. In brief, we say this one MTZ, and then we will be discussing about the breakthrough point, and we will be getting this breakthrough curve from the fixed bed adsorber. Let we can say this if we say this is the say bed, it may be vertical, it may be horizontal. Say for the timing we take this one, suppose this this z will be in this direction, we can say. So, here we can say it is starting from 0 to L. So, in this direction say we can say this one adsorbate is flowing. Okay. And say in this direction we can take in this direction q by q 0, that is we can say at any time. So, how this relative amount of the solute is adsorbed on the surface. So, we can say whenever it will reach its equilibrium, then q by q 0 will be 1. Okay. Let us say we can say concentration of solute. So, in feed we can say let us take this one as C 0, and concentration of solute in bulk gas at axial position Z of this bed from the left to right we can say is equal to say let us say C. Then say concentration of solute in adsorbent in equilibrium with feed, say let us take is equal to say q 0 and concentration of solute in adsorbent at axial position, say at any position z, say that is equal to, we can say, let us take it is q. Therefore, we can say this x prime is equal to say q by q 0. Whatever we have plotted in this y axis, say we can say this is relative amount of the solute, or we can say adsorbed on the adsorbent. Okay. And so, it will be equal to 1 when it is in equilibrium, means q will be q 0. So, that time we can say in this point. So, we can say this q by q 0 is equal to 1. Okay. We can say that is, we can say that these are the general convention for these unsteady state fixed bed adsorbers, and we will be following the same notations, or we can say values for the entire adsorption process. So, let us take this first case like this, bed gets saturated near inlet like this. So, we say suppose through this position the feed is entering with this solute concentration, say C is equal to C 0 like this. Okay. And then we can say whenever we can say near this entry point, we can say when z is equal to 0, say then we can say x prime will be 1, because in that case x prime will be like q by q 0, or we can say this at the entry point the adsorbate concentration will remain, we say we can say this concentration at the saturation point or at equilibrium point. So, that is why in the beginning we can say this one in this axis, we can see this y axis or x prime axis, it will be getting x prime is equal to 1 like this. So, in that case, say whenever it is entering, then say suppose first layer will be adsorbed, first adsorbent will be adsorbed by the adsorbate, then it will go on increasing, or slowly it will be moving like this. When we can say this one T is just leaving the this one, we can say this just leaving the entry point, then T we can say 0 plus, means just after leaving this one. So, we will be getting this type of profile, means say this one say suppose this is just after this entry, and then if we go on increasing this entering the feed, then what will happen when t is equal to t 1 at one particular point, we can say this one the profile of this x prime with distance L from the top of this we can say, or from the entry point of the fixed bed. So, this type of profile will be there like this. So, we can say in the beginning we can the solute concentration or adsorbate concentration will be high, and whenever we will be moving away from this entry point, then we can say constant q by q 0 will be lowering, and one point will be there when it will be q by q 0 is equal to 0, means it is entirely unutilized. Okay. So, in situation B, this suppose this huge amount of we can say solutes have already entered, and the considerable part is already saturated. Then we can say this flow of the feed and the adsorption continues. A section of the bed near inlet gets saturated. So, this portion is already saturated. So, this portion, then we can assume that whenever we say t is equal to t 0, this is the situation like this, when it is like this part. So, with time what is happening from the entry point, all the solutes adsorbing the adsorbate and they will be saturated. Saturated means it will not take further adsorbate this one from the feed. Okay. And if we go on increasing the, we can say this one, if we allow the solute to enter into this fixed bed, then what will happen with time, this we can say saturation zone will go on increasing, and this entry point whatever we have seen this one, it will shift towards the right hand side, or we can say it will be apart from it will move apart from the entry point, and slowly say we can say this one, this is situation, third situation and fourth situation. One point will be there when we can say this, when time t is equal to t b, we can say, then the one part will be there where we can say this one, it can adsorb this entire solute present in the feed. But you see this one, if we wait further, then this we can say this curve will move towards this direction, then we can say the q by q 0 actually will not remain 0 there, it will go on increasing slowly, and slowly means this unsaturation zone will shrink with time, and one time will be there when this also will move from the system, means that the entire this bed actually will be saturated. So, before that we can say this one, thus we can say this one, in the case of the C, the mass transfer zone moves along the bed with time like a wave like this. So, the S shaped curve actually this one, this S shaped curve shown are called this mass transfer wave front. So, this S shaped curve moves from the, we can say, from the left like this, from the left this one to slowly to this right. So, we can say this one, and it will be coming as a wave. So, this is called mass transfer wave front. Okay. And now we will be discussing about one important terminology in the unsteady state this adsorption process, that is breakthrough, means something will be broken and it will be through the we can say bed. So, we will be discussing this one in detail. So, let us take one this one fixed bed adsorber, this is vertically placed, and then say the solute target component is fed from the top of this we can say adsorption column, and the we can say this one, after adsorption whatever is unadsorbed, that is coming out from the bed. Say we have filled this entire bed with this adsorbent, and adsorbate is there with concentration C 0, and say in the beginning we told that say whenever it will enter into this we can say bed, the layers. So, the first layer will be first we can say this one adsorbed, this adsorbate will be placed in the adsorbent site. So, that is why we can say this one, this is we can say the top layer will be adsorbed, and slowly the we can say this one saturation zone will be created there, and then the saturation zone will move towards the entry point to the exit point. So, in the beginning we can say the target component concentration in the exit, or we can say this one effluent will be 0, because you see this one we have selected that adsorbent, so that it can trap fully the adsorbate. So, in the beginning we can say this one, the effluent will contain 0 amount of this target component. So, this is we can say this is designated here in terms of we can say this volume of effluent versus concentration of the solute in this axis. We can say this in the whenever situation A is there, means at the beginning. So, we can say this one concentration of the solute is 0, because here there is no target component or adsorbate here through this effluent. And whenever we are moving from this volume, this one point A volume to say point A to point B, or we can say this one it is moving from this direction to this, then also we can say this one as the unsaturated zone is huge. So, that time also the solute concentration in the effluent will be 0. So, in this position also we can say solute concentration is 0. We are moving further, again we can say this one, whenever we say we just we can compare this one, say from this, if we start from A. So, this zone is we can say unsaturated, then at B position this is also unsaturated zone. So, whenever it will be the we can say effluent will be coming out, there actually C 0 will be 0. Here also this C0 will be 0. Whenever this situation C is there, here also you see unsaturated zone is there. So, here also C0 will be 0. Now, here also in D position we can say small amount of solute concentration in the effluent may be there, because you see it has just touched this, we can say Q by Q0 is equal to 0 point. So, here we can say this C0 we cannot say that it is not equal to 0 or near to 0, but whenever we have this E point like this point, there actually it is not 0. Suppose up to say D point, you can say small amount of the solute concentration is there in the effluent, which is coming out from the this packed bed. Okay. Then when it leaves this one, so if we just consider this point here, you see with time what is happening, the solute concentration is going on increasing from this point to this point. So, one point will be reaching where we can say it starts from here and it is touching this point E, means it is the last point where we can say this one the entire the column is now exhausted. So, there we can say from D point to E, we can say this one just at the end of this packed bed, one particular location where we can say this one it will exhaust in a very fast manner. So, there we can say this one the uppermost layer of the bed is entirely saturated. As the solution continues to flow, mass transfer zone moves downward as a wave, that is we say mass transfer wave front, and one point will be there, we can say this one. So, at D point actually there we can say this one when it this Q by Q0 reaches this 0, and then we can say this one a lower portion of the adsorption zone has reached the bottom of the bed, and solute concentration in the effluent has suddenly risen to an appreciable value of CD. This system is said to have reached the breakthrough, this break point. Means it indicates that in a small period of time the entire bed will be exhausted, then the solute concentration in the effluent risen suddenly and rapidly as mass transfer zone passes through the bottom of this bed. Okay. So, at E point it has reached the initial concentration, because you see this one at E point what happens there, whatever is entering it, nothing is adsorbed on the adsorption side, or we can say adsorbate. That is why whatever is entering the same thing is exiting. So, that is why influent and effluent concentration are same. So, influent concentration is C0, effluent concentration of C0, that is why it is this Q by Q0 has become 1. So, that is why we can say this one this or it has reached the C0 point. So, from E point means whenever the entire bed actually is exhausted, then from there actually we can say the portion of this effluent concentration curve between this position D and E is termed as breakthrough curve. So, this the meaning of breakthrough is that the solute in the feed has been able to break through the barrier of the bed of the adsorbent. So, this we can say that time we can say the time required to reach that breakthrough point is called equilibrium time. Okay. So, or we can say time required to get saturated. So, that is the why we can say breakthrough means this the feed has been able to break through the barrier of the bed. Okay. And after that we will be getting the solute concentration in the influent and effluent as same. Okay. Now, we will be discussing about the length of unused bed or LUB. Let us take this one the last situation, or we can say this one if we go to the situation D. So, there we can say this if we go to this situation D like this one, just to remember this situation D means we can say this one breakthrough will start from here, and then we can say this one Q by Q0 has reached its ultimate point, or we can say this one whatever the unsaturated zone in the column is exhausted, or we can say this we do not have any unsaturated zone, like this type of unsaturated zone is not there in the fixed bed adsorber. So, in that situation we can say this one. So, in that situation suppose here the total system is that the entire part is entirely exhausted, and some portions are there which are not exhausted, but it will be exhausted very soon, and some portions are already exhausted, some portions will be exhausting in a short period of time. Like this, we start from this point 0 to say A prime, then A. In between A prime and A, there is a big long, we can say this one saturated zone is there, that is why you have given one break here. So, we can extend this one, say maybe the big portion, actually it depends on the how long the bed is. So, from there we can say this one from A prime to A, then we can say to D, then to G, to say we can say B to 0. So, let us take this route like this way, this way, this way, this way and this way. So, this is the situation. So, we can say this one this is the entire position of the adsorption system, where we can say this one this used adsorption capacity will be like this, where the adsorption will take place like this, because you see in this zone there will be no adsorption because this is already saturated. So, only in this zone in some portions adsorption will be taking place, in some portions it will be exhausted. Like if we start from this, say if we start from A to D to G to B, say G to F like this, if we start from here like this one, A to D to G to F to E to A, like this one. So, we can say this one, say this portion is unutilized for the adsorption process at that particular time. Okay. And say unused adsorption capacity will be like this, unused adsorption capacity like this, we can say start from, say if we start from C, then C to D, D to say G and then C. This is we can say unutilized or unused adsorption capacity. And you see this, if we cut this part and if we put it here, then say these two portions are same, this portion and this portion are same. If we cut it here and if we put it here, we can say then now it will be like one rectangular part. So, the entire part starting from C, G, F and E, this portion we can say length of unused bed. Okay. Because you see whatever the used portion is there, if we put it here, then it will become unused like this. Because you see from this convention we have taken this y axis as this x prime, this relative amount of the adsorption q by q 0. So, we can say the as the region, this region and this region are same, we can cut this portion say C D G, and if we put in we can say this A E D, then we will be getting this entire zone like this C G F E. So, we can say this is length of unused bed will be like this, we can say will be L minus L S, this portion. Okay. That is why this length of unused bed is this portion. If we say this is x, the direction is x, say this is, we can say this this length actually is not utilized in this particular time frame. Okay. Now, we will be learning about this thermal regeneration of adsorbents, that is simply we can say temperature swing adsorption process also. So, regeneration temperature is selected on the basis of the adsorption equilibria or isotherm at different temperatures. We can say the heat requirement for regeneration is almost 2.5 times the enthalpy of the desorption process. So, this is a very high temperature operation. Then high temperatures are required, at the same time the lower pressure also is required. The technique is called this temperature swing regeneration. So, if we say see this one, suppose this is the adsorption isotherm like this for a particular temperature, say at T A. So, suppose at T A temperature the adsorption isotherm is like that, whenever we place this one partial pressure with this Q in this axis. So, this adsorption isotherm will be like this. let us take this Q0 at any point. So, in that condition we can say partial pressure during this adsorption will be P0. Okay. So, but you see whenever we will be doing this desorption process at high temperature and low pressure, suppose this we have increased the temperature from Ta to Td, then what will happen, this suppose this is the desorption curve. So, in that particular temperature, suppose at Td, so at Td temperature, so we can say this one, this more amount of we can say this this we can say this adsorbed gases will be desorbed, because you see we have increased the temperature from Ta to Td. So, that is we can say more than 2.5 times the enthalpy of adsorption value or enthalpy of adsorption value. So, feed of this Q0, we can say this one feed of Q0 which is there in the adsorption, this one isotherm is regenerated at Td like this one, at Td like this one, and solute concentration reduced to Q1 prime like this. Suppose this solute concentration is reduced to Q1 at partial pressure of P1 like this. Hence, this Q0 minus Q1 like this we can say this one difference actually is removed per gram of the adsorbent during this temperature or thermal regeneration of adsorption process. So, when the adsorption process is over, then this if the temperature is risen from this Ta to Td, and at that condition we can say this one the Q0 minus Q1 amount of this difference amount of the solute actually will be we can say regenerated during this desorption process. Okay. So, that is very much effective, especially for this separation of the gas from the adsorption process. Now, we have this pressure swing adsorption process. This is also very interesting adsorption process, and there are so many applications in the industry. There are 4 different steps for this Castro drum cycle. So, there we have these 4 different steps like this. So, these are the common thing like this. First is this adsorption process. Suppose this is the our adsorber, first adsorber suppose, and adsorption will be done here. Suppose feed gas flows at high pressure through the bed. Suppose we are entering this feed gas through this one, and then say this one inside this adsorption column, the target component will be adsorbed here, and then it will come out as the exhaust gas. Then we need to depressurize this tower. Okay. So, the pressure of the vessel actually is reduced, so that it will be say like this like thermal swing operation, this will be regenerated, that is the second stage. Then some amount of the purging is required. This third step is the small fraction of the product gas which is coming out from that. Suppose this one is again entered to the other bed like this. Suppose this is the now fresh bed. So, some amount of purging actually is done in the second bed. So, that is why we can say this one purging is done. So, the small fraction of the product gas from this bed is passed through the vessel, means to the other vessel. Then we need to do the repressurization. So, feed is supplied. So, no product is drawn during this process. So, now this we can say this repressurization means again we enter the feed. Suppose in this column we again will be feeding this, we can say this one will supply the feed, maybe we will supplying the feed from the bottom of this column. Okay. So, that is why this is called this pressure swing, but in this case 2 operations are there where the pressure is associated. The second step we can say this one depressurization, and fourth step is the repressurization, but other 2 processes are we can say this one in pressure swing adsorption also. One is this adsorption process, the regular process, and then third process is the purging. So, small fraction is purged, but it is not that always the purging is necessary. Now, we will be solving one problem on this we can say in the breakthrough problem, like this adsorption equilibria data for chromium 3 adsorption from a ternary effluent on spirulina platensis is given as follows, where C by C0 in the effluent is given in with respect to time. So, starting time is 10 minute like this, and it continues up to we can say 110 minute like this, and that time C by C 0 was 0 like this first 10 minutes. So, the effluent contains nothing, but you see whenever we waited 110 minutes, then we have seen that C by C 0 or Q by Q 0 has reached this value of 1. So, this is equilibrium data point is already available for this chromium 3 adsorption. Now, we need to this one solve the problem in terms of say breakthrough time calculation etcetera, etcetera. The given parameters are temperature is 20 degree Celsius, bed height is 0.2 meter, then superficial gas velocity is 0.29 meter per second, then C 0 is 0.11 gram mole per meter cube, then bed density is 700 kg per meter cube. If maximum permissible limit is C by C 0 is 0.025, then we need to calculate the breakthrough time. We need to calculate the length of the mass transfer zone also MTZ. We will be getting this one very easily if we are able to plot this, we can say x prime by we can say z. From there we will be getting what is the length of this MTZ. Then using the above data, design a bed for the treatment of 50 meter cube per minute or 3000 meter cube per hour of this effluent if adsorption half cycle is 480 minute, or we can say this one 6 hours, 8 hours, that is allowed. So, what is the average loading of the bed at breakthrough point, and we need to calculate the maximum solid loading at a given inlet concentration of the chromium 3 effluent. Okay. We will be solving this problem. So, we will recapitulate this one. So, firstly we have the C by C 0 data is there with time. So, I think we will be able to plot this we can say breakthrough curve there. So, we will be solving this step by step, we will be doing the solution like the mass transfer wave front, that is we will be drawing this one is drawn by plotting the given breakthrough data like this one. It is tabulated like this, and let us take for solving this problem we need to use the graph paper like this. Say here we will be plotting this time, and here we will be plotting this C by C 0. Then we will be getting definitely we will be getting this type of say S shaped curve, but for the time being, so we are writing this one in the without the scale, but whenever we will be solving this one we need the graph paper. We need to solve this one in the graph paper. Let us take this is 1 and this is 0 and time t is equal to 0, and say let us take say as up to 110 minute actually the data point is given, up to 110 minute data point is given. Say we will take, let us take, we will be taking this up to 120 minutes, say 2 hours we will be taking this one. Before that in 110 minutes it has become 1, C by C 0 has become 1 like this, and then we will be getting this we can say as this we can say this allowable, the permissible limit for maximum permissible limit for C by C 0 is 0.025. So, we can say let us take this for C by C 0 is equal to 0.025, we can say that time when this we can say this one time t will be like this. From here we can say whenever just it will start entering into this we can say the breakthrough curve, like that time we can say this one whenever this 0.025 from here, suppose this is 0.025. So, from this graph paper you find this one, this time will be equal to, so whatever I have got this one is 19.5 this minute. Okay. So, this is we can say this t is equal to say t breakthrough like this. So, this is 19.5 minute. Okay. So, I can say this t b will be equal to 19.5 minute. Okay. So, we got this one from the graph like this. Okay. So, the mass transfer zone, so is not a here actually is not symmetric one like this one, this was not, this is not symmetric one. So, we can say this mass transfer zone. So, whenever we will be plotting this one, we will find that it is not purely symmetric, where whatever we have discussed this one during this mass transfer zone calculation, there it was assumed that it is the symmetric one. That is why say this portion will come and it will be sitting here. So, then unused bed is obtained from here, but in this case it is not symmetric actually from this data points it is not symmetric. So, that is why we can say this one as it is not symmetric. So, we can say this we need to get this stoichiometric time. So, that is why this say time T s actually we can say like this one is say T s stoichiometric time, that is actually is determined by matching the area above the breakthrough point. This for we can say this one T less than we can say this T was T s and that above the curve for T greater than T s like this one. So, from there actually whenever we will be doing this one, that time we will be getting T s is equal to from the graph actually we will be getting is that is 46 minute. Okay. So, we will be getting this we can say this stoichiometrical time that may not be in the middle, but say from this we can say this area under the curve we will be getting this T s is equal to 46 minute like this. Okay. So, now we have this velocity of this wave front is already given. So, velocity of wave front, this u s will be equal to we can say L by T s, that is equal to we can say this 0.2 meter by T s is equal to 46 minute. So, meter per minute. So, that is we can see this meter per minute. So, it is coming out as 0.00435 meter per minute. So, this is we can say velocity of the wave front, we have got this one, this 0.00435 meter per minute. Okay. And this equilibrium time so, T is taken as the time for C by C 0 is equal to, so we can say this one 0.095. Okay. So, for that case we can say this one say 0.95 actually 0.95. So, here we can say, so for this suppose 0.95 and then 0.95. So, at that time actually we can say this one T will be like this. So, T is equal to, so from the curve we will be getting this one that 86 minute. Okay. So, from their curve actually we will be getting this T is equal to 86 minute. Okay. So, we need to get this length of mass transfer zone, that is MTZ, that is nothing but this US into T minus TB. Okay. So, that is coming out as US is equal to 0.00435 into T is equal to 86 minus TB equal to 19.5. Okay. So, from there actually we will be getting this one as 0.29 meter, or we can say this 29 centimeter. So, this length of this mass transfer zone is 29. So, length of unused bed, that is the one question actually is asked, that what will be the length of unused bed, that LUB, that will be nothing but we can say this US into TS minus TB. So, that will be like this US equal to again 0.0435 into TS is equal to that 46 minus 19.5. So, it is coming out as 0.115 meter. Okay. So, LUB is equal to 0.115 meter. Okay. So, that is one this is the answer of one first problem, what is the length of unused bed. Okay. Now, the second problem is, so that is the answer of problem A. Now, we will be solving for problem B. We have to design the this adsorber. Okay. To design the we can say this adsorber, for treating say 50 meter cube per minute or equal to 3000 meter cube per hour this of gas. So, firstly we have to use the same superficial velocity, and that is there in the problem, and then that mass transfer wave front maintains the same shape, actually like this S shape as it progresses. Okay. So, and then we can say this one, we need to get the diameter of the bed from the superficial velocity from the bed will be like this 4 by pi into say 3000 per hour, that is meter cube per second by 0.29 meter per second to the power half. So, that is coming out as 1.91 meter. So, that is the we can say diameter of the bed. So, we got this one at 1.91 meter. Now, we need to get the bed height. So, for that the we can say this one adsorption half cycle is given, is equal to 8 hours. Okay. And so, bed height will be like this total we can say total time into say US plus how much amount of unused bed is there, means how much amount of is utilized and how much amount of unutilized bed is there. So, there we will be getting like this 8 into that US is equal to that is hours a minute into this US is equal to 0.00435, this plus length of unused bed, that is 0.115. meter, this plus 0.115. Okay, so total this height, this in meter, that is coming out as, so bed height is equal to say 2.2 meter. So, this is one answer, and now we need this loading of this bed at breakthrough, that is we need to get loading of the bed at breakthrough. So, all solute actually we can say entering the column in say 8 hours, that is this half cycle absorbed, and say we can say the moles of say chromium 3 entering is equal to say 8 into 60 into this US, say that is 0.29 into say 1 meter square into say 0.11 gram mole per meter cube. So, it is coming out as 919 gram mole. Okay, so, that is we can say this how much amount of moles of the chromium 3 is entering. Okay. So, in the we can say this column. Okay. So, then we have this one total volume of the bed, that will be say 2.2 meter into 1 meter square, that is equal to 2.2 meter cube. Okay. So, mass of adsorbent, because this density is given. So, that wise we can say the volume is known. So, 2.2 say meter cube into density is say 700 kg per meter cube. So, equal to we can say 1540 kg, 1540 kg is there. So, average we can say this adsorbent loading will be like we can say 919 gram mole per 1540 say kg. So, that is coming out as, that is equal to we can say 0.5967 gram mole per kg. So, that is we can say this one average loading. Okay. So, average loading is equal to this one. So, we can say this maximum possible adsorbent loading So, at the end of say 8 hours of cycle, like this half cycle, 8 hour of this we can say this adsorption cycle actually. Then bed length will be so this is nothing but you can say 8 into 0.00435 into 60, that is coming out as 2.088 meter. So, that is actually we can say this one effectively saturated, then we can say this maximum loading will be. So, that is the question, maximum loading will be like this, 8 hours means 8 into 3600 second into 0.029 into 0.11 divided by 2.088 into 700. So, that is we can see this gram mole per kg. So, it is coming out as 0.6287 gram mole per kg. So, this is the last answer, that is what is the maximum loading required for this adsorption process, that is 0.6287 gram mole per kg. Okay. Now, we will be discussing about the ion exchange, the last topic of this chapter. So, ion exchange is a separation process. This is not anywhere related to the adsorption process, but some similarities are there. This is the new separation process. So, it is a separation process in which a solid containing this mobile and replaceable ions is contacted with the solution of an ionizable species. When mobile ions of the solid are exchanged by ions of similar charges like this, so may be positive or negative. Suppose in a solution, say some amount of calcium ion is there. So, we can say this calcium 2 plus will be replaced by 2 Na plus, means their electroneutrality will prevail, but we can say this one calcium 2 plus are free. We will be trapping those calcium 2 plus with the sodium plus, but with the expense of this 2 Na plus in the solution. So, that is we can say this an exchange of ions. So, cations will be exchanged by cations and anions will be exchanged by anions, and the overall charge will remain the same. Okay, this we can say this one number of charge plus number of species, that multiplication value will be same during this ion exchange process. Suppose calcium 2 plus ion will be replaced by 2 Na plus ions, okay, and this resin is R minus. So, this one we can see this one resin part is there. So, using this ion exchange resin, the sodium plus will be replaced by calcium 2 plus. So, we can say we can replace this, we can trap calcium 2 plus using this sodium exchange resin, or we can say the cation exchange resin. So, that is why this sodium plus will be now free, it will be there in the aqueous phase, and then calcium will be trapped in this resin. So, that is why you can say CaR2 will be there, because one R minus can trap one Na plus. So, that is why two resin ions means R minus ions will trap one calcium 2 plus ion. Okay. So, these polymer ion exchange resins are this one huge, like this polystyrene cross linked with a small quantity of divinyl benzene, that is DVB, is a base material like this. A polymer with 10% divinyl benzene content is most common actually in this industrial application also. The ionic sites will be like this, cationic or anionic like this, need to be incorporated in the polymer bed for the preparation of the synthetic ion exchange resin. Like this, whatever this we can this polystyrene is there, what is the requirement, means what type of ion is, we need to trap, based on that the we can say this resin actually will be prepared. Like a cationic site by sulfonation of the benzene rings in polystyrene. For an anionic site like this by chloromethylation of benzene ring followed by the amination, like this one, suppose one polystyrene that is reacted with sulfuric acid to get this we can say strong acid cation exchange resin. Like this, if we want to get this CH3O CH2Cl, then we will be getting say another this one resin with this we can say the anionic part will be there. Like this we can strong base anion exchange resin will be prepared. Okay. And there are so many industrial applications of the ion exchange resins, like the softening and demineralization of the water for boiler and chemical process industries. Then in catalysis also, the like esterification catalyst, like high purity water production for semiconductor industries, like the separation of metal ions from wastewater. Then in electrodialysis, so in so many instances ion exchange resins are used for the separation of different ions from the solution. Now, this ion exchange equilibria reaction can be expressed as like this. Say suppose A plus is there, and then we have this resin, this B plus R minus, and along with this X minus, because A plus cannot be there, because another X minus is already there. So, that is why this A will be now replaced by B, or we can say A will replace B, then new resin will be formed like this A plus R minus, and then B will be free and it will come to the solution like this. So, this A plus and X minus are formed in solution by dissociation of the compound AX like this, and our target is to separate this A plus, means A plus should be freed from X minus. Okay, so, that then we can say we need to add this B plus R minus and then A plus R minus stand for cation exchange resin like this. A subscript this bar on the this, suppose this bar actually on an ion, this one indicates that it presents in the resin phase. So, that is the concentration of the ions in the phase may be expressed in terms of gram mole per liter or kilomole per meter cube or any in other units also. Now, you see this C I is the we can say concentration of the counter ion, this one type I in the solution in gram mole per liter, and say whenever it will C I bar, then it will be say in the resin phase. C also we can see this total ionic concentration in the solution, whenever it is the C bar, then we can say it is in the resin phase total ionic concentration. So, X I is the we can equivalent fraction of the counter ion I in the solution, this Y I will be like this equivalent fraction of the counter ion in the resin, and we can say the charge of the resin is we can say this one I. So, from there we can say this X I is equal to we can say this Z I into C I by C E, and Y I is equal to we can say this Z I into C I bar by C E bar. Okay. So, these are two we can say this one parameters we need to calculate for this ion exchange equilibrium. Okay. So, then we can say this one K A B or rate constant, we can say this for this ion exchange process, that C A bar into C B by C A into C B bar. So, there say if we just expand this C A bar and C B bar, then we will be getting C bar into Y A into C E into X bar X B by C into X A into C bar into say Y B. So, this C bar will be nullified, and C E and C E will be nullified. So, ultimately we have Y A into X B by X A into Y B. Since only two types of the counter ions like A and B are involved, so we can say this Y A plus Y B is equal to 1. Simply we can say this one mass fractions of this Y A Y B will give 1, or that will be say simply X A plus X B will be equal to 1 also. Then we can see this one Y A by Y B like this one, say Y A by Y B is there. So, that will be like K B into X A by X B, just from this equation we can say just by manipulation, or K B will be equal to Y A by 1 minus Y A and divided by X A by 1 minus X A. So, this is we can say this ion exchange resin equilibrium constant K A B, whenever A and B are two ions counter ions. Okay. And separation factors in the ion exchange like this, sometimes it may be favorable, it may not be favorable. So, we can see this if the valency is same, like this for both the A and B valencies are same, suppose plus single cation single anion, or we can see this binary cation binary anion, then K B will be just identical with the separation factor for the ion exchange like this alpha A B will be equal to Y A into X B by X A into Y B. Okay. So, in all the cases we can say this one, if we say this is the favorable one, then alpha A B will be always greater than 1, like this, like 1 alpha AB is equal to 2. So, then we can say it is a favorable one. If alpha AB is less than 1, then we say this process, ion exchange process, is not favorable at all. So, that is why we can say separation factor for the exchange of B ion by A ion will be alpha AB is equal to Y A by Y B by X A by X B. Okay. So, that way we can say this one, whenever this separation factor is greater than 1, then it is favorable, where separation factor is less than 1, that is we can say unfavorable. So, this there are few references like this, DM Ruthven, that is the book written by this Ruthven. The name of the book is Principles of Adsorption and Ion Exchange and the Adsorption and Adsorption Processes, and then Treval's book of mass transfer operations, then McCabe Smith of this unit operations, and B.K. Datta's book of Principle of mass transfer operations. Thank you. So, in the next class we will be discussing the crystallization process, this new mass transfer operation. Thank you.